Hi, I'm Panda, and this is the preview video for the verification and synthesis session at SIGCOMM'. So to start with, let's take a high-level view of what are verification and synthesis, right? And so to do so, we're going to consider two types of things, specifications and implementations. So a specification is something a user, by which I mean a human, writes that says what they desire a computer or a network to do. An implementation, which can either be provided by the user or generated by an automated tool, such as a compiler, is a more fine-grained set of instructions that the computer or network can follow to meet user specification. Given this, verification is the act of checking that the implementation does in fact do what the specification requires. And synthesis is the task of producing an implementation given a specification. Okay, so this seems very vague, so let's make this a bit more concrete. So to start with, let's consider a specification that many of us have seen in an introductory algorithms course, which is we want to find the specification for an algorithm that produces sorted arrays, right? So it says, I take an array of integers as input and I produce a sorted version of this. Now, in terms of implementations, many algorithms do this, for example, bubble sort and quick sort, right? So given this specification and this implementation, verification is the task of proving that, for instance, bubble sort or quick sort do in fact produce sorted arrays. Equivalently, it's the process of showing that no matter what array you give it, so no matter what the size of the array is, no matter what elements it contains, as long as it's an array, bubble sort or quick sort will produce a sorted array, a version of it, right? Similarly, synthesis is the task of taking that specification and identifying these two algorithms. Now, I'm sure many of you have done both of these tasks manually, probably as a part of an algorithms course, right? The difference here is that we want to try and automate these tasks as much as possible. So we want computers to help do this. That's broadly where we are. Okay. Now, this is pretty high level, but in reality, you don't have to have a specification that's quite that abstract. We can also consider the case where the specification is in fact code. So for example, consider a case where we're giving qsort.c, a file that's included in many C standard libraries that implements the quicksort algorithm, right? And an implementation of qsort.c is something that's produced by GCC or a similar compiler, which compiles this code and produces a set of instructions that can be executed by your processor. In this case, again, verification is the task of checking that the machine code does in fact correspond to the C code, right? And synthesis is the task of producing efficient machine code from the C code. Now you might say, hey, when I look at this, isn't synthesis just compilation in this case? The answer is no, it's close, but it isn't exactly compilation. And we'll talk about this in relation to one of the papers that is going to be presented in the session later in this talk. Okay, so now you hopefully have a high-level view of what verification and synthesis are. So given this, you might wonder, well, okay, so verification, I've seen all of these papers for the last several years. It seems useful, but why is it still an open problem? Why haven't we just solved it? Why haven't we found the way to do this for all of our stuff? Okay, so to think about this, let's think about, how you would do this as a human. What is verification? Well, it's the task of proving that an implementation is correct. So let's consider what it would take us to prove that quicksort is in fact a correct sorting algorithm. Well, as a human, what I need to do is I need to think about everything I know about integers and how their ordering properties are. I need to think about arrays and how they work. I need to think about the quicksort loop and how it's moving elements around and combine all of this to write down a proof. Now, a computer cannot do much less work than that. It basically also needs to go take all of these facts and figure out how to combine them in the correct order to produce this proof. And this is pretty hard. Like, there are potentially unbounded numbers of this. How does the computer do this efficiently? So given this problem, we've basically arrived at two broad approaches to doing this in practice. The first one says that, look, it's really hard for computers to produce proofs. So rather than completely automate this, what we will try and do is we'll make it easier to write correct proofs. And the way we do that is through the use of proof assistants such as CCAC or Lean that provide a way using which humans can write proofs and have machines check the correctness of their proofs and also suggest places where the proofs need to be improved to make it easier to check. The other approach is one where we use algorithms that can search for counterexamples. Now, that's a new word. What do I mean by counterexamples? Well, okay, so if you think about it, right, an implementation, for example, quicksort is something that takes an input, for instance, an array, and produces an output, for instance, some sort of, ordered array. Now, the specification says how the input and the output are related, for example, saying that, hey, the output better be sorted, it better have the same elements as the input, etc. Now, if I believe that quicksort is not correct or something similar, there must exist some array for which quicksort's output does not meet the specification. So one way to check that, to verify correctness, is to try and find this counterexample. If I find such a counterexample, verification has failed, I've found a bug. If no such counterexample is found, I have in fact proved that the implementation is correct. So, one way to verify things is to find counterexamples. Okay. In this talk, I'm going to focus on this counterexample-based automated verification strategies, because that's what the papers in this session do. Okay, so how do you search for counterexamples? The most common tool used to do this, and the one adopted by all of the papers in this session, is SMT solvers or satisfiability modulo theory solvers. There are many of them. All papers in this session use Z3. Now, SMT is an extension of SAT solvers, right? And so let's think about how they're used in practice. And to do this, let's do it in a concrete setting where we have some C code, right? And we want to show that this C code has the property that return values are always positive. Now, the way you use an SMT solver is to take this code and this property and translate them into formulas that that SMT solvers can use. In this case, we've turned the return into this variable z, and we've turned the requirement that return values are positive into its negation. So here we say, hey, we want z to be less than 0. And what we can now do is ask the SMT solver to find us a particular value of x and a particular value of y, for which these three conditions hold. Okay, so now let's briefly think about how is the solver going to go about doing this? Well, one thing the solver could do is it could enumerate all possible integer values for x, all possible integer values for y, and check them individually. It should be obvious that that's not very scalable. That's going to take forever, especially in the case where the code is correct. So the other thing that the solver can do is do exactly what we as humans do, which is it can recognize that, hey, actually, I can look at the fact that, look, x plus y is, so you do one thing when x plus y is less than 0, and you do another thing when x plus y is greater than or equal to 0. So I only need to consider one point in both spaces. Also, I happen to know that squaring makes a negative integer into positive. So that's sufficient to show that no such example can exist. This is exactly what a theory is in the satisfiability modulo theory camp, theory term. Theories are this information that allows the solver to efficiently search for these counterexamples. Now, the problem, though, is theories are somewhat limited. And what I mean by that is, consider this slightly more complex example where I'm checking for x squared plus y cubed is less than 7 and then squaring it. Now, even as a human, proving that this code snippet returns positive values is kind of hard. And if I throw this to an SMT solver, it needs to somehow reason about the shape of the x squared plus y cubed curve and what the space looks like, etc. And in general, there might not be any theories that can do this. So we know that certain polynomials, for example, are not solvable with any algorithm. So how do we deal with this? In reality, because of this complexity, SMT solvers cannot always find counterexamples, and a solver can instead say, hey, I don't know the answer. I don't know if a counterexample exists or not. I just give up, right? So as people who are doing verification, we need to work around this. So how do people do that? The most common way to do that is to approximate these. So to take these more complex conditions and turn them into simpler ones. For example, here I've done this simplification where I've noticed that, oh, like x squared plus y cubed less than 7 is only true like if y is smaller than 2, that can be less than 7, but once y exceeds 2, this first equation is always greater than 7, so maybe that's all I need to consider, right? And by doing this approximation, I've sort of reduced the amount of reasoning the SMT solver has to do. However, notice that in doing so, I've also given up fidelity, right? So, x squared plus y cubed less than 7, that doesn't strictly correspond with the case where y is less than 2. And this means that the results return that if when my SMT solver returns a counterexample, it might not actually be a counterexample for the actual problem. So in this case, I'm giving up on completeness. I might say that the program is buggy, even though the program isn't actually buggy. I could also be in a worse situation or in a different situation where the SMT solver doesn't find a counterexample. It says, hey, this thing is perfectly safe, but in fact, there is a bug. So approximations usually require trading off soundness or completeness. And that's the thing that we have to worry about. Okay, so this was about verification. Let's move on to synthesis and why that is hard. Okay, so as a reminder, synthesis is the act of taking the specification and finding a program or finding something that meets this implementation, that implements the specification. Well, okay, so that's roughly the same as writing a proof, right? So if I give you a problem, if I tell you, write me an algorithm to sort integers, what are you supposed to do? Well, you're supposed to go think about how you would write such an algorithm. You are mentally coming up with the steps that you need to do to actually sort an implementation. So again, we want a computer to search through all possible implementations to find the one that best fits our specification. But this is actually quite hard. In fact, there's this question of, from a computer's perspective, what even constitutes the set of all programs? Isn't that a very large set? What constitutes this notion of best fit, and how do we even think about that? And when do you stop searching? Because, there are an unbounded number of programs. Maybe the best fit is some program that you haven't even come up with. How do you even deal with that? And these are questions that people have to address in synthesis. Okay, so again, how do people, I'm just going to briefly talk about some of the ways that people do this. Synthesis is a very wide topic, so I'm not going to cover it in as much detail. So one common tool, which is, I need to figure out what is the set of all programs. One way to resolve that, and a common way to resolve that, is to tell synthesis tools about the grammar or about the types of programs that they can generate. And what I mean by that is, in this case, I'm considering a case where my spec is C code. If my synthesis tool understands what valid C programs look like, it can produce another C program that looks very similar and is made up of valid C instructions. That's one common approach, and it's the approach followed by at least one of the papers we're going to be considering in this session. The other thing with synthesis is a common approach to doing this is to produce a whole bunch of programs and check them to see if they meet specification. Remember, that's essentially the search process. But checking programs is hard. Like, how do you check that a program actually meets a specification? And again, here, most synthesis tools turn to verification. That's why these two topics are closely related. Verification is an integral part of how many synthesis tools work. Okay. So now that we have both of these done, and okay, oh, sorry. So one thing that I forgot to say is, synthesis tools can also use the output of verification tools. So what I mean by that is, in this case, a verification tool would say, hey, these two programs are not equivalent. This implementation doesn't in fact meet the specification. And here's a case where it doesn't, which is x equals 5, y equals -20. Many synthesis tools include search logic that uses this counterexample to actually reduce the set of, to actually reduce the set of programs it has to consider. So this is called counterexample guided synthesis. Okay, so that was about why these things are hard. Now there's this question of, okay, why are we considering this for networks? So the original reason we started considering this is network configuration is quite complex. Networks do more and more things. And that was the original intent for a lot of this network verification work. The thing that's interesting about this year's SIGCOMM is this is, while one of the papers covers, or a couple of the papers cover this is not the main impetus, or this is not the sole impetus anymore. The other thing that has happened that's really pushed a lot of this forward is that networks have become more programmable. They are more flexible, and we're seeing people write more programs for them. So that's made it more important to do a lot of this, a lot of these sorts of verification and synthesis tools. It's led to more interest in this. So that's why, you know, we're applying this to networks. So given this, let's briefly talk about the papers that show up in this session. So the first paper in the session is CCAC. It's from Venkat Arun and others at MIT. And the idea here is that they want to verify congestion control algorithms. So, you know, as you know, these are congestion control loops are an important part of most transport protocols. And what they want to do is check properties or their specifications, such as the utilization provided by this congestion control algorithm in over time is greater than or equal to X%, or there are no packet losses when the congestion window is very small. And what the implementation to consider is specification of the congestion control algorithm written in the CCAC framework. Now, how do they go about doing this, or what are the main things they make? So the first insight they have is that rather than focusing on behavior in some probabilistic model, they just look at the worst case behavior. Now, you might notice there's an asterisk next to the worst case. That's because it's pseudo worst case. There are certain loss conditions that they don't consider because they say, well, every congestion control algorithm does poorly there. And then the second thing they do is, rather than considering a very complex network with many different paths, they find a way to reduce any complex path down to a single, or approximate any complex path using a single path server. So all paths that they consider are no more than 2 hops long. So this is sort of an interesting way to address this problem. The next paper is Aquila, which is by a whole bunch of people from Harvard and Alibaba. So the thing that they focus on is verifying P4 programs that are deployed in switches. Now, what this paper says is, look, there's been a ton of work in the last few years on verifying P4 programs. The problem is that these existing tools are really hard to apply in the context of Alibaba for 2 reasons. One, they're hard for real network operators to use. And 2, they don't quite scale to the complex P4 pipelines that Alibaba runs in production. Right. And so what they want is a nice way to verify all of these P4 programs. Their way of doing this is to develop a new encoding that, when translating P4 programs to SMT formula. So remember, we had to take that C program and translate it into SMT. Depending on how you do that translation, the number of variables and the complexity of the formulas can vary. So they find a better translation. And of course, the other thing that they do that I thought was very interesting is that they talk about how they check the validity, the correctness of their verifier itself. So they talk about using differential testing and other approaches to actually make sure that the verifier itself is correct. The third paper is a synthesis paper. It's called K2, and it's looking at providing efficient BPF programs. So this is one of the differences from compilation that we talked about, and this approach is called super optimization. So K2 takes BPF program and produces another BPF program. Now, why isn't this just a compilation? The thing is, compilers include a set of very deterministic optimization passes that they run. The thing with K2 is it tries to randomly mutate programs. It randomly changes instructions in a way that no human would think is correct. And it tries to then verify that the resulting program is actually correct. So this is called stochastic super optimization and was used in the past for floating point optimizations. K2 applies it to the case of BPF programs. And as a result, it can discover new optimization that no human could possibly have come up with. Finally, the last paper is NoCap, which is from Rudiker and others at ETH Zurich. And the idea here is to synthesize a safe update schedule for switch configuration. So the problem here is that if you have a whole network of switches and you're updating their configuration, the order in which you apply those configurations can impact the correctness and performance of the application. What SNOCAP allows you to do is tell it what updates to apply, what the requirements are, and it can then go and discover tell you a schedule that would meet all of your correctness requirements. And their way of doing this is, rather than considering the set of all updates, they find ones that are dependent on each other, observing that updates that do not depend on each other cannot impact each other, and you can reorder them as you want. After that, they use counterexample guided search, which we talked about before, to then find schedules for these dependent groups. Okay. So as you sit through the session, which I hope you'll attend, the things you should think about is, what assumptions and approximations are each of these things making to ensure tractability, and when do these assumptions break down? The reason you should consider this is they impact the applicability of these tools. The second thing you should consider is, how do these tools scale? In general, verification and synthesis have had severe issues with scaling to real-world systems. How are these tools better at this? Can these tools actually scale to actual uses? And finally, if you want people to use these tools, you need to make it easier for users to write down specifications. Writing down good specifications is not simple in practice. So think about, how easy is it to write specifications? Is there anything that helps you write them better? And these are some questions that you might consider as you listen to these talks. Thanks, and please email me if you have any questions about this talk. Thank you.